All right, so in this video, we're going to do the power series of some functions. But before we do that, I want to remind you of the geometric series. So when you have something of the form, the sum from n equals 0 to infinity of Rn, or r to the n, this is going to be equal to 1 over 1 minus r whenever the absolute value of r is less than 1. So we're going to use this over and over and over again. So let's go ahead and start with some functions that we can work with. So first, let's look at, let's say that f of x is going to be equal to something simple, 1 over 1 plus x. So we almost have this function, but we have a plus instead of a minus. So, but if you think about it, if we wanted that negative r to be equal to x, what that tells us is that r is equal to negative x. So what I can do is I can write it in the form 1 over 1 minus negative x. And then I can plug it in here where r is negative x, and I get this sum from n equals 0 to infinity of negative x to the n, which is also written in terms of a power series, is negative 1 to the n times x to the n. Now what we know is that this converges absolutely on the interval, well, or 4 I should have said. Well, now I wrote it like I'm going to write it on as a set. All the x's such that the absolute value of x is less than 1, which is also an interval that you all are familiar with, which is the interval from negative 1 to 1. And now what happens when x is equal to 1 to positive 1? You get the sums that alternate from 1 plus negative 1 plus 1 plus negative 1, which diverges. And whenever x is going to be equal to negative 1, then this just becomes the sum of 1 plus 1 plus 1 plus 1. It diverges as well. So at the endpoints, we know it diverges. Whenever this is the absolute value of x is greater than 1, absolutely is going to diverge. So we'll say that it diverges otherwise. All right, so that one was easy. Let's do something a little bit harder. So let me erase and I'll be right back. All right, so let's start with another example. So my next example will be finding the power series expansion for the following function. So f of x is going to be of the form something like, maybe let's throw in an x. Well, now it's going to be a 4, and it's going to be 3 plus x squared. Why not? Let's do something like that. All right, so here I want to put it in this form. So it looks a little bit off. Now, r, what can I turn it into? So one thing I'm going to do, I want to manipulate this algebraically so I can get a 1 here. You see, what I need to do somehow is to get a 1. Well, what can I do? I can factor a 3 out of this. You say, there's no 3 here. Well, let's manufacture it. So I'm going to put a 1 artificially here, plus x squared over 3. And then everything here, there's going to be a 4. Okay, so I forced a 1 there where I needed it by factoring a 3 where it wasn't. So what do? Well, now I have that. Okay, fine. Not too big of a deal. So let me rewrite this. I'm going to pull that 4/3 out. The 4 is multiplying and dividing everything. I'm going to pull that part out. And what I'm going to have now is going to be a 1 over 1 plus x squared over 3. Okay, so far so good. It's starting to look almost like what I want. Not too bad. So what would I need? Well, I would need that now this negative r should be equal to that x squared over 3, right? Then if I make that change, I can turn this into 1 minus r. So how do I do it? Well, r is going to be the negative of x squared minus 3. So how I'm going to rewrite it? Well, here we go. I copy the 4/3. I'm going to do the 1 over 1. Now minus, because I needed a minus, negative x squared over 3. So you see, you really are trying to force whatever function we give you, which is going to be a rational function, to look like that. Because then you can use your geometric series to rewrite it. So with that in place, then I can actually write it as the sum from n equals 0 to infinity of, well, I forgot my 4/3. We're going to have to put those. But I'm going to have that term here. Negative x cubed x squared over 3 to the n. And now I have to write the 4/3 that I forgot. So I'm going to put them here somewhere. It's not going to look too pretty, but there it is. All right, so now I can just rewrite it as 4/3, so it's going to look all pretty now. Sum from n equals 0 to infinity of negative 1 to the n, pulling that negative out. And then I'm going to write x to the n is going to be x to the x squared times, x squared to the n is going to be x to the 2n. And then 3 to the n. And that looks a lot better. But now I have to figure out where does it converge. So this one converges on or let's say when the absolute value of x over 3, which is my, or x squared over 3 rather, is less than 1. So that then tells me that this converges when the absolute value of x is less than 3, or, if you will, absolute value of x taking square roots, root of 3. And you see, I have symmetry here, I have absolute values, so I got away without having to do plus, minus, and factoring and all that, because I have the absolute value. And then this is going to be given as an interval. So the interval of convergence is, well, the radius of convergence is going to be square root of 3, and the interval of convergence is and the radius of convergence is square root of 3, by the way, because that's where you're comparing the x in linear form. So the interval of convergence then is the interval from negative square root of 3 to the square root of 3 for the x. All right, and again, as we did before, if you look at what happens at the endpoints, that's positive square root of 3, and then as well as as negative square root of 3, when you square, you get 1 here, then you get negative 1 to the n, which diverges. And whenever the value of x is larger, or whatever value of x you have is larger than square root of 3, or lesser than negative square root of 3, then you're going to have that your series also diverges. So it's going to diverge otherwise. So we have right there two functions that we found their representation in terms of power series. So let's do one more, but in this case we're going to need to take we're going to have to either take a derivative or integrate. So let's go ahead and take a look at that. All right, so now we have the arctangent of x. So clearly we can make it look like this, right? Or can we? Well, we cannot do that one, but we can remember that the derivative of the arctangent is 1 over 1 plus x squared. And that looks a lot more like this, because x, you could pick it to be, or r, sorry, you could pick it to be negative x squared. And you can write it as 1 over 1 minus negative x squared. And that's going to be your r. So you can write this one as the sum from n equals 0 to infinity of negative x squared to the n. And that one will become sum from n equals 0 to infinity of negative 1, and then, whoops, didn't need parentheses there, x to the 2n. But now I put the parentheses, so let's leave it there. All right, and that is going to converge. And converges absolutely too. On the interval x whenever x to the 2n, which is x squared, which is my r, is less than 1. So again, remember that comes from the geometric series test. You need to have that the absolute value of r has to be less than 1. So this is just the interval from negative 1 to 1. I don't write infinity for some reason. Negative 1 to 1. Okay, so that's going to be our interval of convergence. However, that is the series for that function right here. So I have that f prime, which is the derivative of the arctangent, is the sum from n equals 0 to infinity of negative 1 to the n, and then we have our x to the 2n. So how do you go from the derivative to the original function? Well, we're going to have to integrate here. So we're going to have that f of x is going to be the integral, or the antiderivative, from n equals 0 to infinity of negative 1 to the n x to the 2n dx. So now I have the integral of a sum, and you say, wait a second, this is getting weird, and we do need to know a theorem that whenever you have absolute convergence, then you can move this in and out. Only when you have absolute convergence. So that is very important. So I'm going to have the integral here, and I could put the negative 1 to the n out, because we don't want to integrate that part. And now you're going to integrate x to the 2n dx. And now you do know how to do that one, and you're going to have the sum from n equals 0 to infinity of negative 1 to the n, and then x to the 2n plus 1. You add 1 of the 2 exponent, divide 2n plus 1. All right, and you would have to have a plus c. In the video, I stopped here with the series, and then I told you, but I'm going to edit that out, that you get plus c, but the c happens to be 0. And I didn't elaborate on the details as to why, and that's a problem. The reason why that c is equal to 0, and I'm going to now evaluate it, is because this equals to the arctangent of x. And the arctangent at 0 happens to be 0. So when you evaluate this function at 0, notice that you're going to, everything here is going to be 0 because you have x to the power of 2n plus 1. So it's always going, the power is always going to be greater than 1. So you're going to have a 0 for each one of the terms. So you're just adding a bunch of zeros. That's going to give you 0. Now when you evaluate the plus c, well, that just remains plus c equals 0, from where you get that c is equal to 0. That's how you get that c is equal to 0. So the arctangent is just going to be equal to this part on the interval that we spoke about in the video, which is from negative 1 to 1. But my explanation in the video was not great, so I jump in here and explain why. So now on this same interval of convergence, you have that this is going to be equal to your function f of x. So we should make here a point that x is in my interval from negative 1 to 1. But for the moment, that's that. So thank you for watching, and I'll see you next time.